We're now going to do or talk about binomial probabilities. Distribution. For a problem to be binomial, there needs to be two outcomes. Yes or no, true or false, A or B, odd or even, right or wrong, odd or even. And you're going to repeat an experiment many times. The experiment would be guessing on a true-false test. There's two outcomes, true or false. Rolling or die many times. And the two outcomes that we're going to consider are odd or even. Going to do an experiment 10 times, and we're going to decide if it was successful or if it was a failure. For each trial, each time we do it, did we succeed? Did we fail? Head or tail? Going to toss a coin 10 times, and we're going to talk about head or tail. How many heads do we get? How many tails do we get? Now, each time we do the trial, the probabilities have to be the same. If you toss a coin one time, the probability you get a head is a half. When you toss the coin the second time, the probability is still a half. If you toss the coin a third time, the probability is still a half. Remember, the probability that you have 2 boys out of 3 is 3 over 8. You look at the first family and you ask yourself, what's the probability? So the first trial is looking at the first family of 3. And you ask yourself, well, what's the probability that they have 2 boys? The answer is 3/8. You look at the second family that has 3 children, and you count the number of boys they have. Well, the chances that they have 2 boys will still be 3 over 8. If you look at the 50th million family of 3, the probability that they have 2 boys is 3 over 8. The probabilities can change. Now, you may say, well, what are you talking about? They never change. That's not true. So this is not binomial, what I'm going to talk about. Suppose you have a deck of cards, a standard deck of cards. And I ask you, so pick a card. Pick a card, put it back, and pick another card. Pick another card. And keep doing this a few times, 5 times. Pick a card, put it back, pick another card. Well, what's the probability that the first card is a queen? Well, there are 52 cards in the deck, and 4 of them are queens. Let's not worry about reducing them. Now, no. Sorry, don't put it back. Do not put it back. Now, what's the probability? Actually, going to have 2 answers. What's the probability that the second card is a queen? The second is a queen. Well, there are only 51 cards left over. We took a card and we did not put it back. Well, if the card that we took and did not put back was a queen, well, now there's only 3 queens left over. If the card that we picked and put back was not a queen, well, then there's 4 queens left over. In either case, none of these results are 4 over 52. The probability changed. That will not be a binomial problem. Every time you do the experiment, the probabilities have to be the same. They can't change. Every time you roll a die, it's a 1 out of a 6 chance that you get a 4. It won't change under roll. Of course, we're assuming the die is fair. If it's biased, well, it's biased. Chances I'm rolling a 6 might be 4 out of 6. Okay, and it's going to be that way every time. The probability of any outcome cannot change. All right, so now let's talk about the toss or roll. We toss a coin 3 times. Toss a coin 3 times. What is the probability of getting exactly 2 heads? Now, these binomial problems cost heads and tails, 2 outcomes. There are 3 pieces. Now, what's the probability, say, of getting a head, and then a tail? Well, this is a favorable outcome for exactly 2 heads. It's a favorable outcome for exactly 2 heads, because I have exactly 2 heads out of 3 tosses. Well, the probability in the first value is a result of the first toss, namely a head. The second that I write down is the result of the second toss, which happens to be a head. The third result I write down is the result of the third toss, which in this case was a head. The chances that the first toss is a head is a half. The chances that the second toss is a head is a half. The result of the third toss is a tail is a half. We get 1 over 8. But it didn't have to get exactly 2 heads, it didn't have to be this way. It didn't have to be this way. You could have gotten a head or tail and then a head. Probability that the first one's a head, a half. The second one's a tail is a half. The third one's a tail is a half. I meant to say a head. We get the same answer. But there's even another way of getting 2 heads that is 3. You can have the tail in the first position. That is, the last 2 are heads. And the probability of the first toss is a tail is a half, times the second toss is a head is a half, times the third toss is a head is a half. We keep getting the same answer. That adds up to 3 over 8. The thing is, it was a headache doing it 3 different times. What if we want to know the number of ways of getting 7 heads out of 100 tosses? There would be a lot more cases than 3. And we don't want to count each of them or list each of them. Basically, what we want to do is, from this 3 positions, we want to choose 2 of them to be heads. Say the first and the third. And for the record, 3 choose 2. The left number gets factorial on the top. The right number gets factorial on the bottom. And the difference, 3 minus 2, or 1, gets factorial on the bottom. 3 times 2 times 1 is 6. 2 times 1 is 2. Times 1 factorial is 1. 2 times 1 is 2. And we got 3, just like we said we would get. 3 different outcomes. And they're all the same. In fact, this 3 over 8 came from 3 times 1/8. So you have a combination part. Then you have success, and then you have the failure part. Success, the probability is a half. Success is whatever you want, even if it's a bad thing, is what you want. We want 2 heads. So the power is 2. The probability of failing, the probability of having a success is a half. If half the time you have a success, then the other half time you have failure. And how many failures do we want? Well, if you're running the experiment 3 times, tossing a coin 3 times, and you have 2 successes, you want 1 failure. In fact, if you do 3 minus 2, you get 1. And there's your answer. Multiply that out. Okay, let's just do a handful of these. They're all exactly the same, as long as you realize this binomial. And maybe you'll look out and on exams your teacher will say, hint, binomial. Don't take my class though, I won't do that. Okay, so you toss a coin 10 times. Calculate the probability of getting exactly 6 heads. Okay, there are 3 pieces to this answer. First of all, it's binomial, because it's easy to get a head or a tail. You have the combination part, you have the success, and you have the failure. We want 6 heads out of 10. So from 10, we want to choose 6. Oh, and I forgot to mention, 10 choose 6, some review through your teacher and or textbook may write it this way, 10 choose 6. Normally I write it this way, but for some reason I'm writing it that way now. But they mean the same. If you see this, if this is what you're familiar with, anytime I write something like 7 choose 4, please, please think that. Think that. You can do it. All right, the success part. Well, the probability of success, that is getting ahead, is a half, and the probability of failure is also a half. Success. How many successes we want? We want 6 heads. How many failures we want? Well, we do an experiment 10 times. You want to have 6 successes. That means you want to have 4 failures. And for the record, 10 minus 6 is actually that number. And that's the answer. Now, sometimes you may say, come on, this doesn't have 2 outcomes. It has many outcomes. How could it be binomial? Okay, well, let's see. Roll a die 11 times. Calculate the probability of getting exactly 5 twos. The probability that if you toss a die 11 times, or if you tossed 11 dice 1 time, the chances that you get 2s, the number 2 comes up 5 times. Well, you may say, but wait a minute, there's many outcomes. 1, 2, 3, 4, 5, and 6. There's 6 different outcomes. Well, fair enough, but break it up into 2 different types of outcomes. 2 and not 2. The probability of getting a 2 is 1 out of 6. The probability, now let that symbol represent not 2. 1, 2, 3, 4, 5 out of 6 times you won't get a 2. See, even when it doesn't look binomial, spend a second or 2 and think if it is. Either you get a 2 or you don't get a 2. So the answer comes as a product, and if I stress that, you multiply these results, the product of 3 outcomes, with 3 values. The reason I'm not showing you how to calculate these values is because I can't do that. Because each of you have different types of calculators, and even in a classroom setting, without walking around and looking at everyone's calculator, a teacher cannot show how to do it. Generally, in a class setting, what you do is you ask who's, you write down the answer, and you ask who's not getting that answer. And those who are not getting the answer, you look at the calculator, you figure out how it works, and you show them how to do it. Okay, so we're doing an experiment 11 times, and we want to get exactly 5 2s. So that's the combination part. You have the success portion and the failure portion. Success is getting a 2. That happens 1/6 of the time. Failure is not getting a 2. That probability is 5/6. How many successes we want? How many failures? The success is always right there. 11 minus 5 is 6. You want 6 failures. And there it is. 11 choose 5 times 1/6 to the 5th times 5/6 to the 6th. You have to learn how to use a calculator. Let's do another one that would appear not to be binomial. You have an urn, and in the urn you have 3 yellow marbles and 2 blue marbles and 4 green marbles and 1 orange marble for a total of 10 marbles. Okay? Now, pick 5 marbles, and here's the key thing, with replacement. Again, if you do it without replacement, the probability that the first, say, is yellow. Well, there's 10 marbles, 3 of them are yellow. Now, for the second one, if you don't replace it now, for the second one, for the second to be yellow, well, it's conditional. First of all, there's only 9 marbles left. I mean, to equal 3/10, what would go on top? What divided by 9 is equal to 3/10? Well, just bring this 9 up here. Multiply both sides by 9. X would have to be 27/10. Have to be 2.7. Well, trust me, there can't be 2.7 marbles that are yellow out of the 9. Okay, they're not going to be equal. The probabilities changes when you remove something. That is why I'm saying remove it, but then replace it. Take it out, look at it, then put it back. Okay, so depending upon the question I ask, this might be binomial. Pick 5 marbles with replacement and calculate the probability of getting exactly 3 yellow. It's a probability to get exactly 3 yellow. Well, what you have to do is understand this urn a little bit differently. What you need to see in this urn right now for this part of the problem is that you have 3 yellow and 2 plus 4 plus 1, 7 non-yellow. That's what you see. 3 yellows, 3 not yellow. That's binomial. Yellow, not yellow. Yes, no, right, wrong. Yellow, not yellow. There's 2 outcomes. Well, and it's binomial because the probabilities don't change because we are doing it with replacement. Okay, combination, success, failure. And we multiply these 3 results. Combination. From the 5 trials, we want 3 successes. Now, what's the probability of getting success? Well, there are 10. Success is yellow. There are 10 marbles. 3 of them are yellow. Failure. 7 of the 10 are not yellow. And then you have to put the powers. Success. We want 3 successes. 5 minus 3 is 2. We want 2 failures. These 2 numbers should always add up to 5. Always add up to that number. And there it is. And realizing you might not be able to see the power as well. There's 3 and 2. 3 and 2. There it is. Suppose you're taking a true-false test with 10 questions. True-false test with 10 questions. Okay? Taking a true-false test with exactly 10 questions. And passing is 60%. Passing is 60%. Which, by the way, 6 out of 10. If you get 6 out of 10, you pass. Okay. What's the probability that you get exactly 60%? Now, there are 2 outcomes. Either your answer, let me rephrase it. For each experiment, there are 10 experiments. Question 1, what is your answer? You're going to say true or false. That's the experiment. Question 2, or I should say trials. First trial, it will be your answer to question 1, or question 1. Trial 2 would be question 2. Trial 3 will be question 3. There are 10 trials. We're running this experiment 10 times. Okay? And either each trial you are correct in your answer or you're incorrect. The probability that you are correct is 1/2. It's either true or false. The probability that you're incorrect happens to also be 1/2. Okay. 3 pieces. Combination part, success, failure. Probability of success, that is, you want to get 60%. So you want to be right 6 out of 10 times. You want to be correct 6 out of 10 times. Remember, 60% is 6 out of 10. This really says you want to get 6 correct out of 10. That's what it says to me. So you want the probability that you get 6 correct out of 10. So success, you want 6 successes. Failure is also 1/2. And you want to get 4 failures. And from the 10 questions, you want to choose 6 to be right. There are many ways of getting 6 right. You can get the first right, the second right, the third right, the fourth right, the 9th right, and the 10th one right. Or you can get the 5th, the 6th, the 7th, the 8th, the 9th, and the 10th right. Or the 2nd, the 4th, the 6th, the 8th, the 10th correct. Or 1 and 3 and 5 and 7 and 8 and 9. There are many, many different ways of getting 6 right. And the probability of getting those 6 right, or the probability of getting these 6 right, or these 6 right, or these 6 right, believe it or not, they're all equal. So here, I'm just finding the probability of getting any one of these. And then I'm multiplying by the number of times. Remember, if this is 0.2, and this is 0.2, this is 0.2, and this is 0.2, when you add 0.2 to itself 20 times, well, you get 0.2 times 20. Well, this is my 20, say. And what's circled is the 0.2. Okay, and there's your answer. Let's change this problem slightly. You want to pass an exam with 10 questions. They each worth the same amount. Well, you want to get exactly 60%. But this time there aren't 2 choices, A or B or true or false. There's 4 choices, A, B, C, D. 10 questions, multiple choice. 10 questions, multiple choice. Okay. The choices are A, B, C, and D. I'm going to assume that the answers are random. That is, you can't say, well, I know my teacher. She always lets the answers be A, so I'm going to put down 10 A's and I'm going to pass. Or another teacher, B or C has B's come up 80% of the times. Well, pick B. You don't have to study. You can get an 80 without without studying. Just pick B. Or get another teacher. You want a 75% without studying? Just pick D's. No. That isn't the way it is here. The answers are random. You can't say more A's than B's, etc. Okay, choices are A, B, and C. And you want to know the probability that you get 6 out of 10 correct. Now, though there are 4 choices, the outcomes, there's only 2 outcomes. Either you're right or you're wrong. When you get your test back, let's be reasonable. When you take a multiple choice test and you get your question, you get your test back. What you might see is wrong, right, wrong, wrong, correct, 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 wrong, correct. There's only 2 possibilities. Either you're correct or you're not correct. There are not 4 possibilities. There are 4 choices to pick from, but there are not 4 possibilities. Correct and the opposite. Correct is success in this case. In fact, for this problem, I'm going to be a pain and I'm going to check it. You want 6 out of 10 to be incorrect. You want 6 out of 10 to be incorrect. What's the probability that 6 out of 10 are incorrect? So whatever it says in those brackets, that is success. Whether it's a good thing or bad thing, you don't know if it's good or bad, it is success. You want 6 out of 10 to be incorrect or wrong. Well, the probability that you are correct, well, there are 4 choices to pick from, A, B, C, D, and only one of them is correct. The probability of being incorrect will be 3 out of 4 times you'll be incorrect if you randomly guess. So there's 3 pieces: the combination portion, success, and the failure. Combination. From the 10 questions, you want to pick 6 to be right. Now, success is incorrect. The probability you're incorrect is 3/4, and we want 6 of them to be incorrect. Failure. That is not being incorrect. That's the failure. That means correct. That's 1/4. Okay, you may get caught up on this. That'll be too bad. Well, if 6 are incorrect, 4 must be correct. And there it is. You have to be careful about the words. Now, just to point out something. First, let me convince you what I'm saying is true. 10 choose 6, it's this number factorial on top, this number factorial on the bottom, and then the difference factorial on the bottom. Now, if I do 10 choose 4, it's this number factorial on the top, this number factorial on the bottom, and the difference factorial on the bottom. Remember, multiplication can commute. I'm getting the same answers. That is, these 2 are equal. So now if you want to do this problem, if you don't want to get caught up with success and failure, just remember there are 3 parts. Say correct. The chances that you are correct is 1/4. The chances that you are wrong are 3/4. And even if you switch those two numbers, multiplication allows you to do that. Now remember, this one here was correct. If you're going to get 6 wrong, you want to get 6 incorrect out of 10. That means you want to get 4 right. And this is incorrect, and you want 6 to be incorrect. Now, from the 10, it doesn't matter if you put this number or that number here, right here. You can put 4 or 6. After all, they're equal. So if you want, don't even get caught up about, oh my, it says incorrect. That's a negative thing, but this clown and my teacher is telling me that's success. Being incorrect is having success. You know, if that's really, really going to bother you, don't listen to it. Don't listen to it at all. These two numbers should add up to the number of trials. There are 10 experiments going on, 10 questions. Okay, and 6 has to be one of the powers, but it has to go with the one that says incorrect, with the probability for incorrect, which is 3/4. And the probability of failure is 1/4, and you want 4, let's say incorrect, correct. You have incorrect, you have correct. Well, let's change this down here. 3/4 was incorrect, and 1/4 was correct. Well, I clearly said you wanted 6 incorrect. It says it right there. And if there's 10 questions, you must want 4 correct. And then you put 10 choose in here. You put either of those two numbers. It will never matter if you interchange those numbers. It will not matter. I assure you that 100%. It will not matter. Okay, that completes the section on binomial probability distributions. Good luck with them. They're fun. 3 parts, remember.